Guy Hudson from SoilCQuest, a company that is trying to create its own soil carbon revolution for a better planet and farming future. So, welcome to the stage.
Thank you for having me. So I'm pretty confident that all of you in the audience will have seen this graph at some point, right? We're all aware that we're on this trajectory and we've got about 800 gigatons of CO2 budget left to try and maintain our increase of temperature within a 2-degree limit. There's very little that we can argue with this, although I have no doubt that many, many people do try. But at the trajectory that we're currently on, we're looking at about 750 parts per million of CO2 in the atmosphere. Now, the last time we had that was about 50 million years ago in an era called the Miocene. And at that time, sea levels were 40 meters above where they are now. So what can we do about this? Obviously, we are doing an incredible amount of work in terms of decreasing the amount of CO2 that we're putting out into the atmosphere. And this is something that as a nation, we've got to transform industries. We've got to rethink the way that our energy system works, particularly those who are at the center of it, like yourselves in Norway. And we've got to think about how we can bring down the amount of CO2 and other greenhouse gases that we're putting into the atmosphere dramatically. But that doesn't really solve the problem because we're not moving fast enough. And although there's that budget of 800 gigatons of CO2 left to us, there's very little that we can do if we lose it. That's where this blue part at the bottom comes in here. That's for CO2 removal technologies. So not how we decrease the emissions that we're putting out into the atmosphere, but actually how we give ourselves some of that budget back by taking CO2 directly out of the atmosphere. This quote was amazing to me, actually. So we need a negative. This is going to be an enormous opportunity. So forget anything about the climate side of things, even if you weren't motivated by doing that. There's an industry that will be built around this, which is the size of the oil and gas industry. It's a $2 trillion industry that is required to get us back onto a 2-degree path. So how do we do it? Some of you might even be working in these spaces. So there's some really brilliant ideas out there, and there's some slightly quirky ideas out there as well. Everything from kind of solar sails in space to reintroducing woolly mammoths to Siberia. But the more practical ones of them, direct air carbon capture and storage. We engineer our way out of it. We build these massive fans, look a bit like a big washing machine, and we scrub CO2 directly out of the atmosphere. It's a very sensible and pragmatic approach to this. The problem is that it's not really very economical. So we're looking at about $330 per ton of CO2 at scale. So this is a group called Climeworks in Switzerland, who are probably the best at this at the moment. Afforestation and reforestation categorically will have to be a part of solving this problem. But politically, it's really challenging. The last IPCC report indicated that we need to convert an area the size of Argentina to forestry to be able to draw down enough CO2 to remain on their 2-degree scenario. So politically, we're just not going to get to where we need to with that. Bioenergy carbon capture and storage is something that a lot of people have put emphasis on. And it's a really good idea. So basically, we grow plants that create biomass very rapidly, and then we burn them for energy and we pump that CO2 under the ground. The problem is it's even more expensive than direct air carbon capture and storage. So economically, it's going to be really challenging for us. And then there's things like ocean fertilization. So basically, this involves putting iron filings and other nutrients into the ocean to try and create phytoplankton blooms that will draw large amounts of CO2 out of the atmosphere. But it's very uncontrollable, and environmentally, we just don't think we can do it. So there's this stuff, right? Our agricultural soils are in a position which is completely converse to the atmosphere. We've lost 60% of the carbon from our agricultural soils. And soil is the largest terrestrial carbon sink. You've got 2,500 gigatons of carbon in our soil. That's more than all of the atmosphere, all living things, all plants put together by quite a measure. So, how do we take our CO2 from the atmosphere and put it into our soils in a really scalable, adoptable, and economical way? There's a lot of things that we've tried, and there are some brilliant, brilliant farmers working in regenerative agriculture. Probably the best of them, actually, has been just to not disturb the soil as much as we have. So no-till farming has seen enormous, enormous uptake because of the fact that it's economical for the farmer. You burn less diesel, you get out there and you need less people to actually manage your farm. But it's also very positive in terms of building up this soil organic carbon, which is enormously beneficial from an agronomic point of view. Then there's a range of other things that we've been trying. So adjusting the rotations of the crops that we plant to try and increase soil organic carbon. But that means you're making decisions based on your carbon levels rather than based on the economics on your farm, which is really hard for farmers to take up. And there's things like biochar, so adding additives to the soil to try and increase carbon levels that way. But the problem we have with that is we work very hard at adding those additives, but actually a lot of it releases back out into the atmosphere. So what if there was already an answer? There's our SoilCQuest, we work on specific microbial technologies that are used to increase soil organic carbon in a very natural way. And we work with a little fungus here, which is called a melanized endophytic fungus. It's really easy for the farmer. All he does is he applies a seed treatment. He plants what he wants, when he wants, how he wants, in the same way as he always has. And as the seed grows and as the plant grows, so does the fungi. The fungi grows through the soil and it manufactures melanin at a really quick level. And melanin is brilliant because fungal melanin is a polyaromatic carbon. It's a ring carbon. But all that really means is that one of the ways that CO2 gets out of the soil and back up into the atmosphere is stopped because melanin doesn't react with water. The second way that CO2 gets back out into the atmosphere is that it oxidizes, it reacts with oxygen, and the carbon goes back out into the atmosphere through reacting with oxygen and going back out into CO2. But what this fungi does is really interesting. It likes to, kind of imagine a wheat plant. Nice big wheat plant, great big root structure underneath it. You have all these hyphae working out from those roots in a cloud, in a halo around that root structure. And these fungi grow in symbiosis with the plant. So they dramatically increase the surface area of the roots so they can draw up more nutrients and draw up more water. But these fungi really like to deposit the carbon that they create in soil microaggregate. And these are very small, all they really are is very small compressed balls of soil. And they're an anaerobic zone. And we've carbon dated carbon in soil microaggregate back 500 years plus. So this is a really safe place to store that carbon. So we removed the water potential, the hydrolysis, and now we've removed the oxidation. And so what we're creating is a really stable form of soil carbon. This goes back a little bit. So basically, the reason that roots can't get into the microaggregate is they're just too big. So you kind of need the hyphae to get in there. And this is what it looks like. So it's just a simple demonstration. On the left, you've got the plant growing without the fungi. And on the right, you can see that black stuff, which is melanin being created by the fungi, being drawn directly from CO2 out of the atmosphere. The other great thing about this is that we accumulate CO2 as we create a more stable carbon form for storage. So we start with CO2 out of the atmosphere. We add that to water and ions from the sunlight, and the plant creates glucose. That then works its way down through the roots and is exchanged with the fungi, who provide the plant with more water and nutrients through pulling it up through their hyphae and convert it into fungal melanin. But what we've gone from is one carbon atom down to 18 carbon atoms in a stable form that will stay in the soil. What does this look like at scale? Excuse the quality of that picture. In cereals alone, we have 731 million hectares grown each year. Little bit of maths here. Our estimates, in a very conservative way, are that we can create 3 grams of melanin per plant. So we've seen in our studies everything from 17% increase over the growing season to 30% increase in soil organic carbon over the growing season. Really large quantities. But all we're talking about in this really conservative maths is a half a teaspoon of melanin being created in this vast root structure of wheat plants in the field. You multiply that by 1 million wheat plants, which is about the average number of plants per hectare. You multiply that by 3.67, which helps us to convert that fungal melanin into CO2 equivalents, which is the important measure here. And that gets to about 11 tons of CO2 per hectare, CO2 equivalent per hectare being created. Then you multiply that by the 731 million hectares around the world, and suddenly we've got a solution that can draw down 25% of annual emissions. Talking about 8 gigatons per year. And that 800 gigaton budget that we had can suddenly be added to and extended so that we might actually have a chance at getting to the 2.5 degrees that we need to. But it's not just that. So there we're thinking all about the carbon, but we're not thinking enough about the farmer. The brilliant thing about soil carbon is that it's awesome for the farmer. My agronomist mate talks about it as black gold for farmers. It's the thing that all of the productivity from the soil is built on. There was a great quote I heard the other day which was talking about it as the coral reef of the soil microbiome. So it provides all that structure so that the life and the activity in the microbiome that actually helps to add to some of the things we were talking about a minute ago in terms of nutrients and nutrient density in plants, but also in terms of water stress management. So for each 1% increase in soil organic carbon, we get access to an extra 130,000 litres of water carrying capacity in that soil per hectare. So suddenly when you're from somewhere like where I am in Australia, where we're in the worst drought we've ever seen, the water that lands we can manage better and we can provide better to the plants. On top of that, you can use less fertilizer. So if we can increase soil organic carbon, for every 1% increase in soil organic carbon, you also get access to an additional 30 kilograms of nitrogen per hectare. So we've got this amazing opportunity to provide a solution that doesn't just draw down lots of CO2 and pack it stably somewhere where it's going to stay for a long time, but actually helps to increase the productivity of our agricultural soils and to produce more food so that we can manage a growing population. These two samples are a demonstration case where this is literally either side of a fence. And on the right-hand side, you've had a series of melanized endophytic fungi. They're like dark septite endophytes is the wider family. And on the left-hand side, you haven't. And you can just see that rich carbon. Even if you know nothing about farming and nothing about agriculture, it just looks better. Maybe it's because it looks like chocolate, I don't know. But it So how are we doing this? When it comes to biofertilizers and seed treatments, we've been doing this for a long time. We've been applying things like rhizobium, which help to increase nitrogen in the soil, and those are bacteria. It's a very well-trodden path and one that we will follow. The only difference is what they do is they apply a microbial bacteria to increase nitrogen, and what we're doing is we're applying a fungi to increase carbon in the soil. This doesn't look quite as good on the big screen as it normally does. When we're talking about this, we don't just want to focus on that single fungi. The challenge that we have here is that actually no matter how good it is at drawing down carbon, farmers won't see an impact on the year of application. It takes a really long time to increase soil carbon levels to the extent that you're actually able to see some of that benefit. So you're looking at 3 to 5 years. And we really need to get this into the hands of not just that small regenerative minority, but actually the majority. So we've got to create a package that allows them to see an impact in the year of application. And that's what we call SCIP, so the soil carbon inoculant package. In this case, we've created a kind of a microbial stew which we apply to the plants, which includes some nitrogen-fixing bacteria. It includes some of our fungi. It includes some other mycorrhizal fungi. And what we're trying to do is inject the life back into that soil that we've degraded so badly over decades of industrial agriculture. Now, these plants have both been put under water stress. They had about 3 days without water in Queensland in Australia, which is seriously hot, about 35 degrees. And you can see the life of the plant on the right and how it's reacted to that water stress versus the control on the left. What do we actually do? Now, I always find it a bit weird that I'm an Englishman stood up here and I've got pictures of Australian farmers, but my co-founders, this business was started about 5 years ago as a not-for-profit by a farmer and an agronomist who stood up and said, look, do you know what? We're tired of waiting for other people to help us out. We've got to work out how we can actually do this ourselves. And over those years, they have drawn to them an amazing group of microbial researchers, of other farmers, of other scientists, of big corporates and others. And they've worked really hard to build out this emphasis until we started our business about, it's actually about 6 months ago now. When it comes down to what we actually do, so we go out bioprospecting. Firstly, so we go out hunting for these microbes. They're naturally occurring. We know what we're going to look for. We know what we've got to find. We take them into the lab and we grow them up, and we're looking for that racehorse, that one that works best on each individual crop. So we look to tailor these microbial mixes to each of the crops and to each of the situations. We then spend a lot of time in the glasshouse growing these plants out and testing their capacity in more real-world environments, and eventually we take them out to the field. One of the things that we think a lot about is the fact that we really need to get this out there fast. We're on a timeline. We need to get this out, and we need to start drawing down CO2 as fast as possible. And although this product would sell very well purely as an agronomical product, we just don't have we won't be able to scale it at the pace that we need to if we're to do that. So we need to think about it slightly differently. When it comes to carbon offset trading, and I'm sure a lot of you will know about this, there's a really massive opportunity for us to be able to not just provide farmers with the opportunity to increase the productivity and resilience of their soil, but actually pay them to do so that they're turning them not just into farms of the crops that they farm, but turning them into carbon farmers. About 50% of offsets across schemes across the world are above $10 a tonne. So now you imagine at that 11 tonnes of CO2 equivalent that we can draw down per hectare, you're actually providing that farmer with additional revenue of $110 per hectare. And then we can get to the speed that we need to be able to get this out there really fast. Just a little bit about us. So we tried to think creatively about how we could build this business which put purpose alongside profit. And we looked at a range of structures from B Corps to more traditional not-for-profit structures to everything else, but we realized that the only way that we could scale this at the pace that we wanted to was to build it as a startup. But we also really wanted to put emphasis on the fact that we wanted to maintain our mission to draw down CO2 alongside profit. So we made the environment our largest shareholder. We set up our startup and we put the majority of equity into the not-for-profit to represent the people that we represent in terms of farmers and the environment more broadly. I'm a bit over time. That's about it. Fix our climate by fixing our soils.
Please welcome to the stage moderator of this fireside chat, the passionate climate tech innovator Ole Christian Sivertsen, CEO of the Desert Control, the company that's on a mission to make Earth green again. How? By specializing in turning arid soil and deserts into green and fertile land. Please
welcome to the stage. Live here? It's always great to meet passionate people like yourself. I mean, you said it yourself, winning slowly is losing, or a famous Swedish girl said that. So I'm kind of curious how we really, get this at scale. Because you talked about a prospect where you started out with the world kind of becoming an ice age again, and I really think Norway is cold enough already, right? So how do we get this to scale in the scale that you talked about here?
It's a really good question, and for us, we're not going to do this alone, right? And this isn't a silver bullet, and that's the message. I don't want you to take away the idea that this is going to solve all our problems. There was a great quote, which is, there are no silver bullets, but there might just be enough silver buckshot to get the job done. And this is just one of the elements that we've got to get in there. But we're aware that we cannot build this business alone. And so we're working with large agribusiness to incorporate our fungi into their seed treatment so that we don't have to rebuild all of that infrastructure. On top of that, we're producing our own products, and we're working with traditional extension networks of agronomists and farmers and rural retailers to be able to get this out into the hands of farmers as fast as possible. But on top of that, the economics have just got to work. And for farmers, the most important thing is that they're not taking on this burden. And really our aim is to change farmers from the kind of the villain in this climate change story into the heroes. How can we get them to a position where they've got the tools that they need to actually not just provide a solution to themselves, but be the solution for everyone else? And that comes down fundamentally to economics. And there's Mick, one of our co-founders, who's a farmer who works way up in the north of New South Wales, out in a very dry, arid part of the country. He always talks about the no-till movement as a time where he would sit in the pub and farmers were excited about farming again, because they'd gone from a position where they knew they were degrading the land that they'd held for years, and they were leaving their children with something that was less productive than they had before. And suddenly they were doing something that was not just economical to their business, but also helping to improve that soil and to improve the productivity of that land. Now that's a really heady combination. And if we can get that right, then we can scale this out very, very fast.
So I mean, you're addressing some of the economics in order to make it scale, but I mean, as human beings, we're incredible on innovation. At the same time, we are some of the worst beasts with resistance to change that are out there. I mean, how do we overcome the barriers? And let me give you an example, because you talk about your fungi, and then skepticism is one of the typical resistance to change. And you read in the newspapers in the valley area in the US that the fungi on the topsoil is being taken up into the air, and people get what they call valley fever and get sick by this, and then it's a big hooray. So how do we overcome these things?
It's a really good question, and I think the only way that we will get to is education, right? And don't get me wrong, there are always going to be naysayers, there are always going to be skeptics. There will always be those who believe that by increasing the microbial activity in the soil, we may be somehow impacting them. But ultimately, we have to get to a situation where people understand that this isn't something new. These microbes are prolific in our soil. We've just destroyed them, we've degraded them, we've removed them from that ecosystem. And all we're actually doing is we're plugging them back in. And we're plugging in the ones that really work for a particular outcome, both agronomically and environmentally. And so when it comes down to it, I think the skeptics are less likely to be worried about this, because it is very natural. It is something that happens. It is something that is prolific in the soil around the world today. And we just need to work out how to provide ourselves with the benefit and enhance the capacity of that to actually give us a particular outcome.
Yeah. But still, I mean, things that are still natural are still meeting resistance to get across borders, right? I mean, if I try to bring a piece of fresh Norwegian fish into the US or a piece of cheese into Iceland, I'm going to be stuck in customs there. How do you get your fungi across borders and get it to scale?
It's a really good question. So we don't. That's the easy way of doing it. And we realized quite quickly that actually if we wanted to get to scale, we couldn't take an Australian microbe and ship it to the US and ship it to Canada and ship it to Norway. What we actually needed to do was to work out how to find the microbes that we're looking for in each environment around the world. So we don't actually ship microbes around the world. We bioprospect in each region, and we find the natural microbes in that region that are able to have the greatest impact on the most prolific monocultures in that market. And then we grow them from there, and then we actually create that impact there. So we thought long and hard about this, and we're still looking at the potential to be able to take these across borders, but the biosecurity regulations are just too high for us to be able to move fast enough. So we realized instead, if we can mobilize teams in each of these geographies to go out bioprospecting and give them the knowledge that we have, then we can actually get to the stage where we can scale this much, much faster.
Yeah, and I mean, to get to your 25% of the CO2 budget, how much area do you need to cover with that?
So that was done on the basis of 731 million hectares, right? So that is the entirety of the global cereal crop. Like, it's kind of, I don't want to do a Guy Kawasaki if I'd have just 1% of that. But ultimately, for us, the reason for saying that, the thing that's really important, is if with one crop we can bring down 25% of annual global emissions. If we take multiple crops and we work with multiple crop types and we work in multiple regions simultaneously, which is what we're doing, then actually we won't draw down 25%, but we might draw down 2%. And do you know what? Bloody hell, that's a start. We're getting there, and then we can grow from there. We can scale these things from there.
I love your enthusiasm on it. So we got a question from the audience here as well, asking sort of how reversible is the process? Once you've kind of put all that carbon down there, what if you need it back up again?
Again, it's one of those questions that comes up. There are two here, which is, one, how reversible is it? And two, what happens if we draw down too much? And so the first one, we actually need to apply this every year. The microbial environment in the soil is a really competitive environment. You've got everyone competing for the nutrients, for the water, and the fungi that we put in there often don't survive past a year. And one of the reasons that we apply them as a seed treatment is, in applying them as a seed treatment, we kind of give them a little fortress when they enter that soil environment. So they've already infected the plant, they build this mutualistic relationship with the plant, but they can compete in that environment where they otherwise might not survive. So actually these fungi, without the host plant, they're called an endophyte. It's an endophytic fungus. That without the host plant, they don't actually live. And if one of the first things that we do, which is really, really important in our process, is what's called pathogenicity testing. So we basically want to make sure that this fungi doesn't infect anything that it shouldn't. We only want it to actually work within the context of that host plant. And so we select fungi very carefully based on those which will work with that plant. The second question, which wasn't really asked, but I think is quite an interesting one, is what happens if we increase too much carbon? And we draw down too much CO2 and we put too much carbon, and then we start to decrease the productivity of that soil. Now, one, that would be an amazing position to be in, because it probably means we've solved the climate crisis in its entirety. This is it's a really slow process. By degrading our soils, we've gone from productive soils at somewhere up, kind of 5-6% soil organic carbon, down to most industrially farmed soils, which are below 2%. Most are below 1% soil organic carbon. What we're talking about, and our research has indicated, we can increase that by somewhere between 17, 20, even 30% in some of our demonstration trials per year. But think about the base that we're coming from. You're talking about a 0.8% carbon, soil organic carbon, and we're increasing that 30%. So you're only just incrementally increasing this over time. And then even if we do apply this for 30 years, and we manage to get it up to an extent that we've actually got a really high density, we've got back up to that kind of 5-6%, even more, say up to 10% soil organic carbon. The cool thing about the soil microbiome is it kind of balances itself. It's one of those natural ecosystems where the nutrients tend to go to the things that are most needed by that plant. And so actually what's likely to happen is that those microbes will stop being supported by the plant, and it might support more bacteria in that soil to help it get more access to nitrogen. So there's an equilibrium point at which we will actually, the impact of this and the productivity in terms of carbon will tail off, and we'll have the opportunity to be able to actually, that was a long answer to a question that no one asked. Sorry about that.
I mean, you mentioned a lot of techniques and alternative products out there already, and that they're fairly expensive and labor intensive to really work with. Sort of what kind of economical cost barrier do you need to break to really make this a sustainable solution that even a poor farmer in mid-Africa can use?
So when we think about this, it's actually, once you've identified the fungi that works best with that crop, it's actually really cheap to produce these things. So our manufacturing cost is about $7 per hectare. So when you actually compare it to comparable products, similar seed treatments, you're looking at about $10 a hectare. So we can actually create this economically now. It's a very simple process that you basically, similar to the conversation we were just having, you ferment them basically. You think of yeast, it's a bacteria, we ferment them up in the same way we do that with fungi. So that piece is quite easy. The piece that we've been trying to work out is that while with an Australian farmer, we add $10 a hectare to his costs, his input costs in the field, that's about 2% of the overall costs into getting that crop in the ground. So it's very, very small. But as you quite rightly point out, if we're going to do this, if we're going to hit 731 million hectares around the world, we've got to find a way of getting it into the hands of emerging markets farmers as well. One of the great things about this technology is it's really scalable. So whether we're shipping truckloads of coated seed to massive 20,000 hectare farms in Australia, or whether we're shipping tea bag sized packets of seed treatment to smallholder farmers in Southeast Asia, it actually doesn't matter. It's just a seed treatment that they roll it in before they put it in the ground. The thing that we need to overcome in that context, as you say, in the economic piece, is we actually still need to be able, those guys to be able to pay $10 a hectare. And we want to work with a lot of the climate finance that's out there to alleviate that cost. When it comes to developed markets, we think about it as providing the farmer, charging them $10 a hectare and then giving them cash back of up to $110 a hectare. With the emerging market farmers, what we actually want to do is just to be able to provide them with that $110, because then you're getting climate finance to the people who need it most, the people who are living at that intersection of environment and soil, and the ones who are living with the consequences of climate change more than anyone else.
Yeah, I love the idea of kind of combining this with microfinancing in such an environment. So, because you know, you're talking a lot about carbon here, and you mentioned water as well, and in addition to that, you have yields as well. So how do you see this impacting yields? And I think we really need to address this because, I mean, if you look at the IPCC report, WRI and others, I mean, the future looks scary, right? They say if we continue at the degradation level we're currently running at, there will be no more farming in 60 years from now, and we need to increase global food production by 70% by 2050. Yeah. So how do you see this solution playing into that picture?
And look, within the context of this, you need to work on the whole microbial system in the soil, the whole microbiome. We really need to get increased activity there. And for us, it's kind of, it's one step away from a yield increase. Because what we're trying to do is increase that soil organic carbon so that we increase the activity in the soil so that there's more plant available nitrogen. So what we're actually doing directly doesn't impact the yield of those crops. But what we're doing in terms of increasing soil organic carbon and therefore increasing the structure in the soil and increasing the activity helps to increase the yield of those crops. So the stat that I gave around increasing plant available nitrogen for each 1% soil organic carbon increase, that's what really helps us to increase yield rather than necessarily what we're doing directly. But there are wonderful people such as yourself who are helping us to create more agricultural land so that we can actually start to rebuild the productivity of the world as a whole in the agricultural soil context.
Yeah. No, and of course it will contribute to yield increases because, as you say, well, I'm focused on really creating soil out of sand and recreating some of the areas that have degraded completely. And I mean, we've seen the enormous importance of really stimulating the fungal activity in the soil, because the fungus there, they are the natural extensions of the roots of the plants and whatever, and without them you can't really take any nutrients in. So that was the reason for my question there.
Absolutely. Yeah, no, I totally agree.
So I mean, we definitely need to talk more, later on how we can make these fungi of yours live even better by maintaining a moisture level and stuff like that. I'm really excited about this. So what is the current situation with SoilCQuest in terms of do you have live customers? You have revenue? What's your funding situation?
So we're a really early stage company, right? So we worked as a not-for-profit for a long time. We were extremely resource constrained, and it took some, and I'm not just saying this for the sake of it, but it took some really brilliant investors who saw the vision of what we were doing to help actually ignore the fact that we were a slightly awkward structure and to help actually support us to build this business. So we are about 18 months away from our first product. 18 months to 2 years. My Chief Product Officer hates it when I say 18 months. 18 months to 2 years is the kind of the boundary that we've given ourselves. And so we're continuing our work in the field, we're continuing our work in the lab. We're always continuing our work in terms of building our isolate library, building the library of different fungi that we work with. And so we'll be working out, and then our aim is to have that product in the market in 2 years.
In 2 years. Are you funded to get to your 2-year mark now?
So we closed our seed round recently, so we raised about $8.5 million, and that will take us through to that first product.
Yeah. And from that first product, sort of when will the hockey stick kick in? And
this is the other really cool thing about agriculture, is adoption rates are really, really fast. So there was a whole bunch of modeling that was done around this product by a group called adoption rate modeling around agriculture products by a group called CSIRO down in Australia. And their prediction was that you could get to something like an 89% adoption rate within 6 years, because those extension networks in developed agricultural markets are so strong. And the agronomists who work with the farmers through to the rural retailers back up through to the agribusinesses, if we can leverage all of those and we can use that infrastructure, then the adoption rates, I don't know whether it's a hockey stick or a rocket ship, but either way, it's very quick.
It's for sure a game changer, right? Yeah. So another question from the audience here. So could you apply some of these principles and the fungi technology to hydroponic systems?
I'd have to ask our agronomist. I think, I don't know actually. I've never thought about it because we always think about this in context of increasing soil microbial activity. Now, in the context of hydroponics, we obviously don't have that. We just have a nutrient mix that the plants are growing in. So I don't know quite why we would do that, because effectively you'd be drawing down carbon and then maybe as a runoff from the hydroponic. I don't know. Interesting question. Not one I've had before.
Good. I mean, we're into anything hydro here in Norway, so you have to expect a lot of questions there on how we can do it into even maritime areas. So good. I think you spent a little bit more time, so I think we may be already over time here. But this was extremely exciting, and I'm looking forward to head down under and discuss more on how we can do this together.
Thank you.